Hello, everybody. Nice to meet you. This is Simone Tiozzo, and I'm the coordinator of research and development activities in Stazione Sperimentale del Vetro, the Italian Glass Research Center. And I have the honor of being the moderator of today's event. And so, let's please just before introducing you to the four amazing speakers that we will have today presenting their projects or their activities or their outline on the decarbonization of the glass industry sector. Please let me thank, first of all of you again. Let me join Cordula in thanking you all for joining this webinar, thanking the speakers, and thanking also Steinbeis and Cordula for the great organization of this event. So what are we talking today about? Today we're talking about the decarbonization and of the glass industry and the efforts that the whole chain is doing for making the target of net zero emissions of 2050 become a reality. Of course, as all of you know, the glass production industry is an energy-intensive industry, and it's a hard-to-abate sector because a big amount of energy that is required for the melting and production and forming of glass comes nowadays from combustion of fuel. And of course, today it's of fossil fuels, so with associated carbon emissions. But the sector has been doing a lot of activity of research or development, developing projects and making big investments in technologies and radical changes for the future in order to comply to the CO2 emission targets that have been put by the European Union onto the whole industry. Okay. And in this sense, in a way, so it's the industry is trying to work out a way to reduce its burden on the emissions. But it's also true that the industry, the glass industry, and the glass products that are made by them are becoming great enablers for the decarbonization of the whole society, from energy saving measures with the glazing, and the ECU and coatings sophisticated for the solar control or low emissivity of glasses, the wind turbines made of fiberglass reinforced plastics, and so on and so on. Glass is becoming an enabler for many types of decarbonization technologies for other sectors. So in this regard, I think that I would like to introduce to all of you Bertrand Cazes, that is the Secretary General of Glass for Europe, the Association of Glass Producers of the Flat Glass Sectors, that is going to give us its experience and its overview of the glass industry as a whole in its journey towards carbon neutrality. And so please, Bertrand, I leave the floor to you. You have 10 minutes. Thanks a lot.
Thank you, Simone. I am actually very thrilled to be with you this afternoon and to hear those three specific projects. And the reason for it, these three projects are trying to address one of the biggest challenges of our time for the flat glass sector and the flat glass industry in particular. Now, indeed, decarbonization is a challenge, but is also a chance for this industry through the products, and you mentioned it, and that's what I will focus on this afternoon. But I hope with this introduction on the contribution of glazing and how we put that into the broader vision of the role of the flat glass industry in a climate neutral Europe, we give even more prominence and importance to the work that is being carried in those three specific projects to try and help decarbonize the flat glass industry. Now, we always talk about decarbonization, but it all sounds obvious to us, but I like to put it into a broader context. I mean, why is it that we are talking about it? We are talking about it for climate reasons. We're talking about it for environmental reasons. It's in fact the life, the nature, and the life of all of us that we are talking about at the end of the day. And it is true that in the flat glass industry, because we are a global material with global impact, we have our share of responsibility in making the efforts necessary to change things for the better. Now, I could say this is the headline of the presentation. Flat glass is a material that is key for climate neutrality, for circularity, but also for many other aspects, digitalization, safety, health, innovation. I will come back to that. But I mentioned at the start that this is one of the biggest challenges of this industry for the time, and therefore for a trade association of a European scope, like Glass for Europe, it is our duty to support the flat glass sector throughout this transformative journey. And we do this working with both upstream flow glass manufacturers, the main ones in Europe, as well as a myriad of national associations from the glass processing industry. Because in the flat glass sector, you have an entire ecosystem made of the production of the upstream material, but also all its transformation into those end products, valuable end products that we need for decarbonization. Now let's have a look at what's happening in buildings with flat glass. Different researches and work were done, and those showed that actually high performance glazing can help cut around 37% of the CO2 emissions from buildings in the EU when we look at what the situation could be in 2050. And that is, of course, thanks to the high performance insulating glass units that we put into buildings and the novel technologies that will keep coming up if we're talking switchable glazing, but there could be others in the remit of building integrated photovoltaics as well. Now, one could question how we've calculated those 37%. As I said, this is a maximum saving potential that was calculated by an independent research institute called TNO. And you have on this slide all the references if you want to look at this report. You look at what the building stock is today and the glazing that is installed on this building stock. And you project what the savings would be in 2030 and in 2050 using high performance products. For 2030, you use available high performance glazing. For 2050, what you project being the performance glazing back in 2050. And then you are reaching those 37% in terms of energy saving. We are also then able to project what it means in terms of reduction of CO2 emissions, depending on the energy mix of the different European countries. And you have here the results on slide. So a massive energy saving potential if we upgrade buildings with high performance products, because unfortunately nowadays a lot of European buildings are still equipped with old generation glazing, which are not up to the standards today. So that is a massive contribution when you think of it. 37% of the largest source of CO2 emissions in Europe could be saved thanks to glazing. And that is made possible because this industry has heavily invested over the last decades on product performance and has developed products, high performance glazing products, which have a much better energy performance than it was decades ago. So you see moving from single glazing to double glazing to coating, double glaze coating, triple glaze coatings, different types of coatings. And of course they are new innovations to come. So first of all, a massive contribution that this industry can provide to decarbonization efforts in the building sector. But as the industry provides this improvement, it is not, forgetting the fact that there are plenty of other benefits that it has to bring to buildings in terms of protecting the indoor environment, the health. It has contributions to make in terms of acoustics, in daylights, in winter comfort, summer comfort, security, safety, and so on and so forth. And I think this is an important item to mention, because at the end of the day, we're building buildings for people to live, work, play, heal in those buildings. And that is the primary reasons why we do this. And of course, we have to keep doing that as we minimize environmental impacts. Sorry. So this is certainly a big area and contribution in buildings. But next to building, there is the contribution in terms of solar energy. Photovoltaics, for instance. If you think of photovoltaics, you might not realize it, but between 65 to 95% of the weight of a PV module is made of glass, a very specific type of glass that is low in iron to maximize conductivity, very often with self-cleaning properties. And then you have also a big glass contribution to solar mirrors. So it's not only about saving energy, the contribution of glass, it's also about helping to generate a renewable electricity. So another important area. Mobility, automotive in particular. Yes, automotive is made of a lot of flat glass. And in fact, we see modern cars, and particularly electric cars, on average, have a bigger glass area than in the past, thanks to the contribution in terms of bringing the weight down, thanks to the contribution in terms of efficiency and range, thanks to advanced coating, and thanks to the integration of all the automated driving components within the glass surface of a vehicle. So also a product coming in there with important contributions. But it is clear, once all is said, that glass and flat glass is an energy-intensive manufacturing process, and therefore some work has to be done there as well. We've never hidden away from that reality. Now, once you say that, you need to know where you're starting, and the starting points are there. A lot of improvements have already taken place. You see minus 43% of CO2 in 25 years per ton of flat glass, thanks to industrial innovation, energy-saving technology, an evolving energy mix, improving circularity. And so some good steps have been done, but still we need to go faster and stronger in reducing CO2 emissions from the industry. I will just probably finish with this slide, because we've done already a number of years ago, 5-6 years ago, a big exercise to try and quantify where are the biggest potential for saving CO2 emissions in flat glass manufacturing. And of course, nothing novel here, but the biggest potential lies in CCS/CCU, but that it is an extremely difficult approach, and then in switching the type of energy you use, using more renewable energy and in particular electricity, but also potentially hydrogen. I know some of the projects we're going to hear about today are tackling this specifically. So again, this to highlight how important the matter is. And recycling, you see here a much lower potential, simply because the availability of glass for recycling theoretically is constrained, but this is probably the most activable way of reducing CO2 emissions in the short term. So all of this is precisely to say what you're going to be discussing today is right on the topic of what matters for this industry. So I'll leave it up here because this was just a short introduction, but just to say that this change that we have to go to a sustainable low carbon building is of course a driver of added value production for the glass sector. And indeed, this industry takes it as its role to manufacture those products needed for this transformation in the most sustainable way. And that is why we need all of your research, your testing to succeed. And then, as the title of this webinar says it well, we need to make sure that this can then come to the market. And I'll leave it here for the introduction. Really looking forward to hearing the next speakers.
Well, thanks a lot, Bertrand, for this great introduction to our more technical sessions. This was a great overview of what the flat glass sector is doing for its own emissions and for what it is enabling other industry sectors and the society as a whole in doing for the rest of the emissions. So thanks a lot again. And now we go towards the most technical part of this webinar, and we will have 3 presentations by 3 European funded projects, which all deal with efforts, technology, science efforts in reducing the CO2 emissions of the production of glass. And in this sense, we would like to start from the most research-oriented project, the one which is a bit more far from the market realization, but that is indeed studying a very, very interesting, radically innovative potentials for enabling, for example, recycling of glass in order to increase the circularity, and through circularity, as we know that recycling glass allows to achieve energy saving and thus also emission saving, achieve decarbonization. I'm talking about EVERGLASS project, and today we have with us Jozef Kraxner from FunGlass of the Research Center of Trentin, that is working inside the project, that is dealing with this new technique and technology for that it could enable the recycling of what today are difficult to recycle glasses, like borosilicate glasses or specialty glasses, etc. So please, Jozef, tell us what you are doing inside the EVERGLASS project to make this a reality. You have 15 minutes. Thanks a lot.
Okay, thank you so much, Simone, for your kind words. And now, can you see my presentation? And also, can you hear me? Okay, perfect. Thank you. One more time. And really, it's a pleasure for me to be here today. And also, thanks again for the nice introduction. And as was mentioned, my name is Jozef Kraxner. I am part of the FunGlass Glass Ceramic Research Center from Trenčín, from Slovakia. This is a very small city close to the Bratislava on the west part of Slovakia. At this institute, I am the leader of the glass processing department, and today I would like to deliver to you a basic introduction about the running European Union project EVERGLASS, which focuses on the development of innovative glass recycling technology process. A little bit a different topic, is not completely focusing on the decarbonization process with some fuel changes or some another optimization process into the melting process, but directly we are focusing on the recycling or upcycling process with a different way. Okay, so now just I would like to start with some general information about how much glass is produced worldwide. Every year, approximately more than 130 million tons of glass are manufactured. However, only about 27 million tons of this amount are actually recycled. This means that the remaining 103 million tons is approximately 21% tons ends up as waste. Most is going to the landfill and simply waiting for their end of life instead of being reintroduced into the production cycle. Over time, unused glass accumulates, taking up valuable landfill space and contributing to long-term environmental issues such as a contamination of water, air, and etc. Definitely, this amount of the glass deliver us, how to say, huge potential, which can be is very important topic related to the application and also related to the scientific point of view. And also on this slide, I would like to deliver you just a basic information related to the statistical information related to the recycling process at the European level. You can see that the average glass recycling rate across the European Union is about 76%. The different colors shows how far each country has progressed towards to the 2030 glass recycling target. Some are already very close or achieved, while others still have a significant gap to close in the coming years. The best countries are indicated in green, for example, France, Sweden, Finland, and Italy, and the weaker ones like Hungary. As you can see, in case of Hungary, just only 30%, but in case of the France or Italy, is approximately around 81%. It is wonderful. But definitely, the position of the European Union is very good into the container glass recycling process in soda lime glass system. As I mentioned, is on the level approximately 76%. When we compare Europe with other regions, we can clearly see that there's still a lot of room for improvement worldwide. In countries such as the USA, Canada, China, or India, the recycling rates for glass containers are significantly lower. For example, for USA, just only 35%, for Canada 30%, China 20%, for India approximately 45%. This shows that glass recycling is not only an environmental issue, but also a very important scientific and technical challenge. We need to ask ourselves how we can develop new processes and technologies to deal with this problem and increase the recycling rates into the future. To give you a better feeling for the scale, more than 28 billion glass bottles and jars end up in landfills every year. That is such a large volume of waste that it would fill to Empire State Building. In addition to the standard soda lime glass, there are many other glass types that are much more difficult to recycle. For example, borosilicate glass used for cookware and laboratory equipment, or some special glass. Special glass has a much higher melting point and very strict purity requirements. It means very sensitive for the melting process, to keeping some redox state without incorporation any inhomogeneities and so on. Another type is a glass fibers used in the insulation, and composites are coated with organic part that burns off and creates byproduct during the melting, and can create some lot of small bubbles, and also can decrease the final quality of the final produced glass fiber. Another type is the electronic glass, often contains heavy metals and special coatings that interfere with the normal melting process. And finally, the last group can be created unica or special glasses, which has very different melting points and compositions. So if they are enter a conventional recycling system, it is very difficult. And also is very important to here to mention that is very important to introduce some very high recycling system, which can make a good separation based on the chemical composition, which is not simply process. And this brings me to our motivation. Looking at these challenges, we started asking ourselves two simple but very powerful questions. First, is it possible to develop alternative ways of recycling glass beyond the conventional remelting routes used today? And second, could we design a process that also allows us to recycle other type of glass, not only standard glass containers like soda lime glass, but also technical and specialty glasses that are currently excluded from most recycling streams? These questions led to the idea behind the EVERGLASS concept. Once we had this idea, we also need to find the right source of the funding to develop such a high-risk, high-gain concept. That is why we decided as a consortium to submit our project to the EIC Pathfinder Open Call, which specifically supports radically new technologies at very early stages between the tier level between 1 and 4. The 4, it's mean the process or the techniques should be validated at laboratory and environment. It was not easy. The proposal was successful only our third submission time, but is the good in this European call that every year the call is open and you can make a resubmission of your modified project proposal. But in the end, EVERGLASS was selected for the funding. Here on this slide, I would like to, a little bit introduce our consortium. The coordinating partner is the University of Vigo in Spain, with the leading of Professor Juan Po and Rafael Comesana, and they are responsible for the development of the laser technology and the processing roads for glass. The second important partner is the CSIC in Madrid, plays a key role in collecting and classifying a different glass system and in studying their chemical composition as well as their chemical and physical properties under the group Professor Alicia Duran, Maria Pasqua. And the third important company or partner is the Actalia. Their role is to make some evaluation related to the life cycle assessment so that we can evaluate the environmental and economic impact of the EVERGLASS concept. Another partner is the ESCI, the European Science Communication Institute, is responsible for the dissemination and outreach activities. The fifth partner is the FunGlass, which focuses on the analysis of the 3D printed glass objects, looking in detail at their chemical, optical, and other physicochemical properties under the leader of Professor Dusan Galusek. And finally, Fraunhofer supports the project with the advanced numerical simulation using the mesh-free approach to model and optimize the process, because we have a different important parameters where at the beginning of the EVERGLASS project, it would be very helpful if we can get some on the theoretical level, some basic information. Let me briefly summarize the basic facts about the EVERGLASS project. The project runs for 36 months from January 2024 to December 2026, and the consortium has received almost 3 million euros of funding from the European Union. We are currently in the second year of the project, close to the end of the second year. In total, 6 partners from our countries are involved, and more than 30 people are actively working on EVERGLASS, including directors, group leaders, professors, researchers, PhD students, technicians, and administrative staff who support the project. So, the long-term vision of EVERGLASS is to develop a technology that can turn different kinds of glass waste into tailor-made products. We call this concept glass laser morphing, using laser-based processing to reshape and reconfigure waste glass instead of simply melting everything down again. The idea is to extend the life of existing glass elements enable integral glass recycling, and finally create new customized glass components directly from waste, and to create a new product with added value. Very briefly, let me say a few words about EVERGLASS methodology. Here you can see a simplified concept of the EVERGLASS fabrication process. A laser beam is focused by the optics onto the surface of the substrate. By precisely controlling the position of the focus and the movement of the substrate, we locally melt the glass and create a new part of the glass. The first EVERGLASS processing concept, which was developed at the first year of the project, was based on the off-axis powder feeding configuration. In this step, the precursor glass powder is transported by the carrier gas and injected from the side into the laser-induced melt pool on the substrate, with the assist gas helping to stabilize the process. This arrangement allowed us to demonstrate the basic feasibility of glass laser morphing, but it also showed some limitation in terms of symmetry and surface quality, because it's very important to make an adjustment related to the laser beam and the feeding process into the same on the same level, and which later motivated us to move to the coaxial feeding system, which was developed in the second year of the project. But in this configuration, you can see the laser beam and the powder feeding system remain in fixed, stable position. Only the substrate is moved, and it can move into 3 directions along the X, Y axis in the plane, and in the Z direction to build up the height of the glass part. The controlled motion allows us to create the glass structures layer by layer, like common, additive manufacturing process. As you can see, the process is very simple. And as I mentioned, the precursor glass powder is injected into the laser beam. It melts on the surface and forms a small molten pool on the substrate. In this way, the 3-dimensional glass part grows directly onto the substrate, and to create the new 3D glass object without any polymer is used in another additive manufacturing techniques like stereolithography, direct writing, or fused deposit modeling. And later on, as I mentioned, during the second year of the project, the coaxial concept was developed, in which the powder feeding and the laser beam are both oriented into the vertical position. The precursor powder is delivered into the coaxial stream around the laser beam, creating a well-defined interaction zone and much more symmetrical, stable process for building the 3D glass part. And here, on this slide, you can see a short video of the real fabrication process of the glass part. In this case, the object is made from the borosilicate glass, and the whole build takes only a few minutes, as you can see now. Just only the substrate is moving, as I mentioned on my previous slide, and the laser and the feeding process is completely fixed. And as you can see, this is the fabrication process. And during few minutes, it can be produced a very nice new part, as you can see also on the right side. Of course, all the processing parameters are extremely important: the particle size and the size distribution of the powder, the laser power, the scanning speed, the step size of the substrate, and so on. At the moment, we are working on optimization strategies to find the best combination of these parameters, because our goal is to understand to what extent we can fabricate glass objects with tailored properties, from porous structures to fully dense and even transparent components. At the moment, I'm not able to share with you more partial results, because we are into the submission of some patent and publications, and for that I would like to keep some IP protection. Just definitely later on, anybody can contact us directly, and we can, share more partial results. But as I mentioned at the beginning, this is really revolution idea, because we would like to focusing on some not easily recyclable glass system. And now I would like to make a short conclusion. First, the EVERGLASS project is exploring the new technology for glass recycling. We are trying to show that laser-based processing can open up completely different routes for giving glass waste a second life. At second, our aim is not to replace the existing glass recycling infrastructure. Conventional remelting of container glass works very well and should continue. Instead, EVERGLASS is meant to complement this method and add new possibilities where today's technologies reach their limits. At third, we are particularly interested in the recycling of hard-to-recycle glasses, such as the borosilicate and other technical glass systems. These materials are currently largely excluded from standard recycling streams, and within EVERGLASS, we are investigating how they can be transformed into the useful, high-value new products. And with that, I would like to thank you for your attention, and definitely I will be happy to take any questions. Thank you so much for your attention.
And thanks a lot in turn to you, Jozef, for this overview of the EVERGLASS project. I think that is very interesting what you're doing, because that's true. Recycling glass can allow to extend the circularity in terms of resources, in terms of not using virgin raw materials to create glasses. It allows to reduce pollution, to reduce the disposal of glass into, not pollution, but it's the disposal of glass into landfills, which but the problem is that for many types of glasses nowadays, there does not exist a system of stewardship for the collection, the separate collection of glass. We have it for container glass, but for example, we have it in limited ways, not with the same type of development for some flat glass products, but we don't have it, for example, for borosilicate glass. And probably what you are developing right now in your project, thanks to what you exactly said, the possibility of creating an upcycling solution for borosilicate glass might foster the development also of collection circuits, collection systems for this kind of glasses. And so this can help in fostering this kind of beneficial effects at the European scale, and why not maybe even further, as you've seen that there is a lot of potential for the implementing in many other parts of the world where recycling is not at the same level as in the old-fashioned Europe. So now we're switching to another project, which is the GIFT project. And we have with us Nerijus Striūgas from the Lithuanian Energy Institute. It is going to tell us what their project is doing in tackling some different aspects of decarbonization of glass production process. It's not by enhancing circularity, in this case, it's really dealing with how energy is brought to the melters, and in the sense, in using some, let's say, tapping into not yet used streams of renewable energy that nowadays cannot be used as they are, but maybe with the technology they're developing, there will become a new potential source of energy, green energy, for the production of glass in the future. So, Nerijus, you have the floor, 15 minutes for you. Thanks a lot.
Okay, thank you for kind introduction. I hope you can see and hear me. You can see my slides. Yes, okay. So, as was introduced, I am Nerijus Striūgas from Lithuanian Energy Institute, and today I'm going to present you our European project, which was funded by Horizon Europe program, and it is dealing with sustainable glass industry with a fuel flexible technology. So first of all, I would like to introduce our project. So the project is a 4-year project, and we started in the 2023 in October, and this project received some amount of money for sure. It was about close to 5 million euro. As I said, we are coordinating it. And on board, we have 9 partners from different countries as well. So from Sweden, we have Chalmers University of Technology. From Germany, we have Technical University of München, Vytautas Magnus University from Lithuania. As well, we have companies which are dealing with dissemination activities, VIP from Germany. We have 2 industrial partners, one glassmaker from Lithuania, Panevėžys Stiklas, and another one is a shot from Germany. As well as we have small SMEs, small companies, Plasmair from Germany, and we have a university from Sheffield, United Kingdom. So what the GIFT is dealing with. So as you heard today, so the glass melting is one of the Europe's most energy intense industry. And here it's produced a lot of CO2 emissions as well. So, and how you saw, the production is, it's growing or stabilized, but we still produce a lot of glass products in the Europe. And this glass production is very high energy, requires energy. So especially glass melting, where the process takes at 15 or 1600 degrees C, and accounts for over 75% of the total energy requirements for the glass melting. And you can see some numbers here that the final energy consumption for this project is quite huge. And another fact is that this energy industry still depends on fossil fuel, mainly on natural gas, and it consumes a lot of it. So therefore, we have a high carbon footprint for this process, and only from the combustion process, CO2 emissions comes in close to 75 to 85% from combustion, while remaining part, about 25% comes from the decomposition of carbonates. So, yeah, and what is the problem the GIFT addresses? So, as we heard that there are huge attempts made recently to reduce CO2 emissions in this industry, but still there are requirements or new solutions are required. So, and not only one measure can be applied, but we have to couple different measures to reach this decarbonization in this process. So first of all, we can apply green electricity, then we can apply circularity process, green alternatives to replace natural gas, but this requires a hybrid fuel scenarios. That means flexibility in extremely challenging situation, especially in energy market, when the fuel prices can be different for different fuels, for example. And if we act in this situation, we can select the best fuel for that situation. Okay, so what the GIFT proposes, what solutions? So GIFT aims to create flexible hybrid furnace or combustion process or process that replace natural gas with biogenic residues and green electricity and unlocking low carbon heat production. So let's say that we have energy market which has different bioresources, renewable electricity, green fuels like hydrogen, or natural gas, which is used now. And if we have in the market situation low biogenic residues with low cost, so we can introduce them and produce syngas via gasification processes and use these gases instead of natural gas and burn it inside the furnaces to create the heat needed for the process. And for example, if we have cheap renewable electricity, then we can switch to more electrical power usage. So that means that we have to introduce two new developed products like hybrid plasma burners, which consumes electricity to create a flame, or we can also boost the gasification process with plasma gasification system and produce more syngas with using electrical power. And if we have hydrogen, then we can switch completely to green fuels, to zero carbon fuels, and minimize CO2 production from the process. When we are changing the fuels, for sure some parameters inside the furnace are changing, and the main parameter which plays a huge role inside the high temperature processes is flame radiation, which needed to know and which needed to be studied, and it will done in this project. And if we have, for example, biomass ashes, so then we can replace some natural ores and therefore reduce energy demand as well as CO2 emissions. And here you can see which partners is responsible for which part of the project. In the GIFT process, we are dealing with different scenarios. So here is presented the main scenarios or existing one when the natural gas is used. So it's typical process for the production of, for example, of container glass, and we did different mass and energy balances to figure out which process and what where can be applied and how it deals with the energy demand and with CO2 emissions. And here you can see the base numbers for the natural gas. And if we switch to biomass case, then we have to introduce some new technologies to the production side. So that means all system parts needed to make syngas or producer gas, which can substitute natural gas. So that means that we have to introduce not only gasifier, but also the biomass processing production for this process. For sure, the energy demand doesn't changes, but CO2 production or emissions changes. It increases, but if we say that CO2 coming from biomass is neutral, then we can save a lot of it. Another scenario is a green electricity scenario. So when in the market we have a lot of, or not a lot, but a cheap electricity, then we can switch to use more electrical power in our plasma devices. So then we can boost our both combustion process with the plasma energy coming from electricity and gasification process we can boost. In that case, we can reduce fuel consumption because we are submitting electrical power, and for sure, in that case, we are reducing CO2 emissions. And finally, if we have hydrogen, then we completely can switch off biomass case and move with hydrogen to boost our process to carbon zero production, at least from combustion side. And GIFT expect some numbers which we are calculated from these studies. So you can see the energy consumption, it's not so huge reduction, but for CO2 emissions, which comes from the glass melting process, we can expect quite huge numbers, especially when we are using hydrogen. The green one shows the carbon neutral fuel, so emissions. But the most important fact is that we can save about close to 50 or 40% of fuel consumption when we are switching to plasma assisted combustion mode. So that means that part of fuel we can substitute with electrical power. And and key innovation of our project is plasma assisted biomass gasification. This will be tested for entrained flow gasifier in the TUM, in the Technical University of Munich, and there is responsible partner, and Plasma Air, which supply the plasma torch for this process. A hybrid fuel flexible burner will be developed at Lithuanian Energy Institute together with Plasma Air and Chalmers Technical University. Flame heat radiation parameters will be deeply studied by Chalmers University together with Lithuanian Energy Institute, and biomass ash gasification as a feedstock for a glass production will be studied or is studying in the Sheffield Hallam University in the United Kingdom. Okay, and the most interesting part is we are now in the middle of the project, so we have some nice pictures at least. For sure, we cannot go in very detail, but here you can see some visual comparison of conventional combustion and hybrid burner flames. For example, in the top of is a combustion process, and on the bottom you can see when we make a combustion with 50% of electrical energy and 50 comes from fuel. Here you can see the plasma torch in operation, and the schematic representation how it looks like. So the plasma is made from the oxygen, which is a plasma forming gas, and the combustible gas which was tested till now was hydrogen and methane. And here you can see as well the plasma torch power and the main electrical parameters which are for this burner prototype. As I said, we did a lot of efforts in the radiative properties understanding. So here you can see different instruments, how we applied to test these plasma torches for plasma assisted combustion. And we are lucky and stabilized this process at this high temperature. We operated with both fuels, achieved radiative and temperature conditions comparable to conventional combustions. And here we can state that the hybrid plasma burner has huge potential for technological solution to bring electricity into crown heating of the glass furnaces. And the final slide is a nice slide from Sheffield Hallam University, where they are playing around with ash for substituting in the glass making process. So here you can see different examples and some numbers, or at least how much is expected to replace and how much we can reduce of CO2 emissions. And very nice point is that they collaborate with some artists, and they created these artists created very nice glasses and exhibited in some exhibitions. So it's very interesting and nice application for now. And as I said, we are in the middle, and what next? So we have to finish with the experimental trials, finish with the modeling processes, make a huge testing to validate our plasma assisted combustion at shot glass melting furnace, techno-economical analysis for sure, and optimize of glass batches and composition with additions. So thank you for your attention. And if you are interested in our project, you can follow us using this link.
And thanks again to you, Nerijus, for this very interesting introduction to your project. And I think that this kind of technology is quite interesting in that it enables really a new type of renewable energy to come into the glass melting world, okay? Because right now we have been using biomethane, biogases made on purpose, etc., as a sort of renewable fuel, okay? But in this case, we can use solid biogenic residues, okay, for melting glass, which is not possible by themselves, because if you burn you can make glass with pellets or with chips or wood. So in this sense, this technology could enable this new source of renewable energy to be tapped into and contribute to the decarbonization of the glass sector. And also the plasma-assisted torches, burners, could really be an interesting solution that maybe we should talk about later, also because we have a question about that, but that will be posed in the ending Q&A session at the end of the presentation by the three projects. So now, remaining into the matter of green fuels, but switching to another type of green fuel, that is hydrogen, I have the pleasure to introduce you to the Chiara Caccamo. She is the coordinator of the H2 Glass Horizon Europe project, of which also my institute is taking part to. And she will introduce what inside this big project with a lot of industrial partners and the research institute, etc., we are doing to try and foster the development of the technologies to enable the hydrogen combustion in the glass industrial world. But this is not only a green transition project, but it's a twin transition. And also this project features digital tools, digital twins, smart tools for the implementation and optimization of these new technology measures to enhance the sustainability of glass production. So Chiara, again, 15 minutes for you. The floor is yours. Thanks.
Thank you very much, Simone, for the kind introduction, and good afternoon to everyone. I'm glad to speak about the H2 Glass project that I'm coordinating on behalf of SINTEF Energy Research. Today, I will give you an overview of the project, a few about the trials ongoing, a bit on the combustion technologies, but then I've been also asked for this session to focus a bit on the twin transition part of the project, like Simone highlighted, where we will speak about also the digital technologies we are developing and we will be testing. So first of all, why we decided we made this project to address the glass decarbonization challenge. And this is because glass is an important material for our everyday life. It plays a central role in sustainable and circular economy, and it's important for new low carbon and energy efficient applications, like we have seen. Glass is also a very important industry for Europe, generates work for more than 400,000 people, high revenue generation business, and it also emits about a bit more than 20 million tons per year. We have also a replication case for aluminium, and this is why it's mentioned also into these numbers. How we do that? We wanted to cover the full technology stack required to replace methane with hydrogen, and we wanted to do it in a way that ensured the required product quality and that ensure safety into the industrial plants. We have 23 partners in this project from north to south of Europe. It will last for 4 years, actually a bit more than 4 years. And it's a project overall budget of 33 million euros, 24 funded by the European Union. We started in January 23. Indeed, we will have soon next year, beginning of next year, our second project review with the European Commission. how H2Glass is pursuing his objectives. First of all, we gathered key industrial players that are really pushing forward the state of the art and have been working with the hydrogen technologies since some years. We work also with the technology replicability for the aluminium sectors, and we cared about involving European industrial associations in order to ensure the desired impact. We are working with solutions that potentially can be retrofitted into the existing industrial spaces. And to push the TRL of the technologies we are working on, we decided to perform trials at scale using a 2.5 megawatt electrolyzer, which will give us some room for long-term tests with significant results for the industry itself. As anticipated, we have also dedicated work around the digital technologies, and special focus is given to safety and risk management, given the handling of hydrogen. A little bit about the trials. We started quite early, end of the first year, with some preliminary trials with hydrogen in trailers. Why? We did that first to have confidence on the pipelines, equipments used, the setup that will be then used also for the trials with the electrolyzers, and in order to produce some preliminary results when it comes to burners and a few data regarding also the impact on the products. These trials have been executed in 2 plants until now. One in a couple of tests were performed in Owens Corning in France. And here you can see a few screenshots from the test trials that give the flavor, the complexity of these field activities. We did the same in the Steklarna plant with a 1-year distance from each other. During these trials, for a few hours, both companies reached 100% hydrogen in at least a couple of burners. And in particular, Owens Corning, which was testing with the hybrid furnace, could reach really the maximum CO2 abatement during those tests. Results are promising, and we are waiting for the longer term trials with the electrolyzer in order to confirm some of the results from this test. At the same time, we are also performing other lab tests to complement and increase the confidence in the results we are achieving. A little bit now about the combustion technologies. The burners are developed by our partners Staraglass, while CHIB is taking care of the control system. These burners have been developed both for oxygen and port furnaces. The prototypes have been already developed and tested. Now we are undergoing the scale up and industrialized version for the full scale tests. These burners will be then tested in the 2 pilots in Italy, in Vetrobalsamo and Zignago. One characteristic of this system will be also the regulation of the various parameters during the ramp up, or let's say the change in the mixture between methane and hydrogen, as these burners are supposed to work with any mix of fuels. With regard to the furnaces, we are working again, our partner EVERGLASS is working to define the ideal characteristics of the future hydrogen furnace, focusing on the upgrades compared to the current state of the art. The two furnaces under analysis are again regenerative and oxy-fired, and the study, which is involving also several external experts to the project, include furnace materials and insulation, geometry, combustion geometry, the burners, as we have already discussed, and additional safety aspects. But now I'd like to give you a bit of an overview regarding the digital part of the project. So we have dedicated a full work stream to these activities where we focused on several aspects. First, the creation of a data architecture for the collection, storage, and access of the data and the metadata produced on site. The partners are working to create several types of digital twins in order to enable preventive maintenance strategies, but also to optimize production, planning and control of the overall system, including increasing the automation level of the furnace and combustion system. Another part of the work is dedicated actually to the flexibility of the overall system, so the process and the energy fuel mix, in order to provide services both towards the internal processes, but also to the external network operators. Activities are also dedicated for assessing the quality of the final product as impacted by related to the use of hydrogen, and to a vision system for the hydrogen flame inside the furnace. A big part of the work, the first year and a half, has been indeed to understand the type of data collected and how to create a flexible architecture and data infrastructure, leveraging on the cloud-based technologies. So a lot of the work has been the identification of the requirements and specifications, standards and protocols to assess and for the data handling. And here you can see how the work has been designed, giving, of course, a lot of priority to the security aspects for what regarded the data handling. The digital twins, that's in progress. So the point is to have good interfaces and having the possibility to transfer this data from the sources to the machine learning and the AI modules that will then present results in dedicated dashboards. And here again, as anticipated, some of the work is dedicated for predictive maintenance operation and scheduling, together with smart production planning and control, where we work also with simulation-based digital twin models and multi-objective optimization. When it comes to automation and control system, the main objective is to improve the existing glass production automation, especially to optimize the quality during the production changes and to minimize energy waste. So in this respect, partners are working on this furnace design and simulation software, which is implemented to produce an empirical formula able to estimate furnace consumption based on several parameters as listed here, not going one by one. Since this is quite relevant today when we speak about energy flexibility, since, as explained, the project is going to deal in a way with the electrification, as the hydrogen will be produced using an electrolyzer. Part of the work is indeed dedicated to start possibilities for services provision, which would also give a possibility for additional revenue stream, exploiting the potential flexibility of the overall system. In the end, other activities is dedicated on the evaluation of the impact of hydrogen on the product quality, and this is done on the hot side, as explained, creating a system for monitoring the and on the cold side in order to monitor defects in glass, but also part of the work will be dedicated to develop prediction models for glass quality that goes beyond the test data sets available. And this is a work that is being done in cooperation between Pilkington and University of Nottingham. This is all on my side. Thank you very much.
And thanks back to you, Chiara, for this comprehensive overview of all the different topics that are being developed at the same time in this very big endeavor that is the H2 Glass project, with 23 partners from all over Europe interacting every week, every day, to try to bang our heads together and find a solution for really enabling this future possibility of hydrogen combustion. Because on one side, we have to say that, of course, we are studying this, but we know that there is no infrastructure, no grid, no yet, okay, for the production of green hydrogen and the distribution of green hydrogen throughout Europe. But if this becomes a reality towards the future, then we will need to be ready for technological solutions that allow us to exploit this possibility. And this is the real reason why we're all working on this kind of innovation. Not innovation; it's a real research and development project at the highest of the TRLs of the three now projects that we have presented today. So we've come to an end to the technical presentations that we've had. Thanks to I would like to thank again our three speakers that have introduced their activities